So up until now, you've seen at least two examples of simple harmonic motion, an object that falls through the center of the Earth, and a mass on a spring. We've also hinted at the pendulum as another example of simple harmonic motion. Here's yet another. I want you to picture a wheel that's rotating at a constant angular speed of omega in a counterclockwise direction. And then I also want you to picture just the ground, the floor below. I'm not sure that's really horizontal, is it? Fix that. Okay. Oh, while we're at it, let's picture one more thing. What if you attach some object? I don't know what it is. Maybe a ball of clay. I don't know. Something you stapled or taped or glued and affixed to the rim of the wheel. And so it's going to rotate along with the wheel with the same angular speed omega. Now, let's take it to another level here and imagine, what if you had a bunch of light shining down from above, the lights from the ceiling, so that you can cast a shadow of this object that's stuck to the rim of the wheel. What would that look like as time goes by? As the wheel spins with this value of omega, what would be the resulting motion of the shadow of this object attached to the rim of the wheel? So after a little bit of time goes by, our object started here, and with the passage of time it'll have advanced through some angle theta. By the way, theta would just be equal to omega times t, and at that point our object would be here, and if we draw a line straight down, I guess its shadow would be located here. Let's go a little more in time to where the angle theta is pi over 2, or 90 degrees. So now the object is here on top of the wheel, and of course if we project down to find where its shadow would be, it would be lined up right there with the center of the wheel. The farthest to the left the shadow ever travels would correspond to the point in time when the object attached to the wheel reaches this position here, and we draw a line down, and there we have it. So in fact, I think this represents a sort of equilibrium position and a negative amplitude, and over here a positive amplitude. In fact, I think the motion of this shadow as it zips across the floor would look just like a mass vibrating on a spring. Let's check that out. So we'll say the floor just represents some sort of an x-axis. Let's look at this in more detail. I see a right triangle, so zoom in on that. That dashed line represents the motion along the circular path. So this is nothing more than the radius of the wheel. There's a right angle, and then this position right here is just some random value x. Keep in mind x is at most positive a and at least negative a, but x is a variable, and x is the instantaneous position of the shadow, and so we're imagining the object when it gets right here. So this value is x, and it's subtended an angle of theta. I think x is just equal to the radius of the wheel times cosine theta, but theta is omega t, so x equals r cosine omega t. What about the speed? Well, that's dx dt, so the speed would be equal to negative omega r sine omega t. What about acceleration? That's the second derivative of position with respect to time, and it would give us negative omega squared r cosine omega t. But of course that just means that the second derivative of position of the shadow with respect to time is equal to negative omega squared times the position. omega is 2 pi times frequency, or in other words, frequency is 1 over 2 pi times omega, and period is equal to the inverse of frequency. So our period would be equal to 2 pi divided by omega. If we compare all this to the mass on a spring, we see a lot of similarities. If I pull the mass back to here and let it go, it vibrates back and forth past the equilibrium position, starting from x equals positive a, and after half a cycle, x equals negative a, and we guessed that the position as a function of time is equal to a cosine omega t, and found this only satisfies Newton's second law if omega is the square root of k over m, and therefore the period is 2 pi times the square root of m over k. Let's take a look at what the velocity must be as a function of time for the mass on a spring. We just need to take the first derivative. So we get v equals negative omega a sine omega t. And the acceleration as a function of time, take the derivative yet again, and we get negative omega squared a cosine omega t. But that in turn is equal to negative omega squared times x. So notice what we have. An equation for the velocity of a mass on a spring, and we also have an expression for the speed of the shadow along the ground. You can see the similarity. In fact, they're the exact same equation, provided that r and a mean the same thing. But of course they do. For a shadow moving across the ground, the amplitude is nothing more than the radius of the wheel. After it's gone through this angle theta, there's the radius, but originally the radius is here, and that's nothing more than the amplitude of motion. So the motion of an object on the rim of a wheel is just periodic. There's nothing simple harmonic about it. It always has the same speed at any point when the shadow gets, or when the object gets here on the wheel. Its velocity vector, v tangential, points this way. The speed is just the length of that vector. It's the magnitude. When the object's here, it's still the same length vector when the object gets here. So there's no change in the speed at all for the actual object. However, its shadow has a speed that varies in time according to this equation. We can graph position, speed, and acceleration the position, assuming we begin timing the moment that the object is at this point. So we'll say that's t equals 0. Then the position of the shadow on the ground as a function of time is just a graph of cosine. Let's translate one full cycle onto all these graphs. Okay, velocity as a function of time is a graph of negative sine. And acceleration as a function of time should produce a graph of negative cosine. So all three quantities, position, speed, and acceleration, are all sinusoidal. And they all cycle somewhat out of phase with one another. When the position is a maximum, the speed is 0, and the acceleration is a minimum. When the position is 0, the speed is a minimum, and the acceleration is also 0. When the position is most negative, or at a minimum value, the speed has a 0 value and the acceleration has its most maximum value. So they're all cycling, but they're cycling somewhat out of phase. The same thing we see is true for the mass on a spring. Position, speed, and acceleration are all sinusoidal, either cosine, negative sine, or negative cosine, and they all cycle out of phase with one another. So something to carry with you in the rest of this unit of study on periodic motion, and in particular simple harmonic motion. The graphs that describe position as a function of time for anything that follows simple harmonic motion are always graphs that have some sort of sinusoidal shape.